Welcome to the deep dive. For a long time in applied statistics, we were really focused, maybe too focused on just simple tests.
Right. Like just getting that p-value.
Exactly. And we often left the deeper story hidden inside our models kind of untapped.
Yeah, and that's become more obvious recently, hasn't it, with things like the replication crisis?
Mm-hmm. It's really put a spotlight on how easy it is to misinterpret results if you don't understand the model itself.
Precisely. And that's the core issue, isn't it? We build these increasingly complex statistical models, which are, the backbone of modern data science.
Sure.
But getting clear, interpretable answers straight from the model parameters, that can be really tough.
It's like having this super powerful engine, but you can't quite read the dashboard properly.
That's a great analogy. And that difficulty, that lack of a clear way to read the output, well, that's frankly made misinterpretations more likely. It feeds into those replication problems we mentioned.
So that's the challenge, getting trustworthy insights from these sophisticated models. How do we actually tackle that?
Well, this is where some tools can really help. There's a fantastic R package called modelbased.
Model-based. Okay.
Yeah, and it's designed specifically for this to help you sort of tame and understand and really harness what your models are telling you.
So it's like the user manual for that complex engine.
Kind of. It gives you this unified interface, makes it much easier to pull out the really important stuff. Things like predictions, marginal means, marginal effects.
Okay, wait, let's break those down. Predictions seems like a natural starting point, right? What does the model actually predict?
Exactly. That's often the first question. Model-based helps you get those expected outcome values for specific predictor combinations.
But it's more than just a single number, isn't it? There's uncertainty.
Right. And crucially, it helps you distinguish between confidence intervals, that's about the uncertainty in the average prediction for a group, and prediction intervals. Those are wider because they account for the variability of individual data points. So it tells you the likely range for a single new observation. Things like the estimate expectation function handle this.
That distinction is super important. Confidence versus prediction intervals.
Mm-hmm.
Okay, so predictions give us specifics. But what if we want a more general picture, the typical outcome for a category, averaging over other things?
That's exactly where marginal means come in. They're really useful.
How do they differ from just, say, predicting at the average value of everything else?
Well, instead of just fixing other variables at one level, marginal means calculate averages by sort of integrating over the distribution of those other variables. You can do this based on your actual data spread that's called empirical.
Right.
Or using a more balanced, idealized grid, which gives you theoretical averages. It gives a much more representative picture. Think the average petal width for each iris species, considering the typical range of petal length, not just one fixed length.
I see. So it averages out the other influences in a smarter way. Okay, so you get these average levels for different groups. The next obvious question is, are those averages actually different, statistically speaking?
Exactly. And that leads us straight to marginal contrasts. Model-based has functions like estimate contrast specifically for that.
To quantify and test the difference between those marginal means, like comparing iris species A versus iris species B directly.
Precisely. And then closely related, you have marginal effects. Sometimes people call these slopes.
Okay, so means are about the level, effects are about the change or the relationship.
You got it. Marginal effects tell you about the average relationship. How does the outcome change, on average, when a predictor changes? This is especially key when you have interactions in your model.
Interactions. That's where just looking at single coefficients can really lead you astray.
Totally. Marginal effects help you understand how that relationship itself might change depending on other factors, but it gives you the average slope. It cuts through that complexity.
It really sounds like model-based gives you a much clearer lens, almost like X-ray specs for your model's behavior.
Yeah, that's a good way to put it. And it even lets you choose how you want to calculate that average picture, using what it calls marginalization types.
Oh, what are the options there?
There's typical, average, and population. Typical uses means or modes for the other predictors, like assuming a standard balanced scenario.
Okay.
Average actually makes a prediction for every single row in your original data and then averages those predictions. So it reflects your specific sample's distribution.
Right, weighted by my actual data points.
Exactly. And population goes a step further, kind of simulating a broader population, which can be useful for certain causal questions. This flexibility means you can tailor the analysis to what average means for your specific research question.
That's quite powerful. And what about more complex setups, like hierarchical or mixed models? Does it handle those?
It does. There's estimate group level.
Yeah.
And it's particularly useful there because it uses something called partial pooling or shrinkage.
Shrinkage, what does that do?
It basically means that for groups where you have very little data, the estimate for that group gets pulled slightly towards the overall average estimate across all groups.
Ah, so it stops you from making really extreme conclusions based on just a couple of data points in one small group.
Exactly. It makes the estimates more stable and reliable, less prone to overfitting, especially with limited data in some categories.
So wrapping up, it feels like model-based really pushes you beyond that simple, is there a difference, yes or no question.
Absolutely. It helps you understand what that difference looks like. Is it a difference in the average level? Is it a difference in how one variable relates to another across groups, like comparing average petal widths or seeing how the petal length width relationship changes per species? It allows for real nuance.
It lets you see the whole picture of the model's behavior, not just isolated parameters. So maybe the final thought for your listening is this. Given that we can now get this more holistic view, how might that change the way you look at your own data? What deeper truths might emerge when you see the entire system the model describes, not just the individual parts?